What is the definition of an increasing function? Yes, Station?
As the x value is increased, so does the y value for increasing.
Yes. So in previous grade, okay, even if your teacher told you about the gradient, that definition was a calculus definition. Remember, differential calculus is about gradient. So if you're given a definition based on gradient, that was a calculus definition. Okay? Now, in general, in the lower grade, that is 10 and 11, an increasing function is a function such that as the x values are increasing, the y values are also increasing. Okay? That's a simple definition from lower grade. A decreasing function is one whereby as x increases, y decreases. Okay? Now, in this grade, we are going to define now an increasing and a decreasing function based on gradient. Okay? So, let's talk about increasing function. Increasing functions. Increasing function. Is I want to write this point down. A function f is strictly increasing. A function f is strictly increasing. A function f is strictly increasing over the interval AB, like that. The function f is strictly increasing over the interval AB if f prime of x is greater than 0, if f prime of x is greater than 0 for all, right, make sure you write it like this, for all x is an element of AB. Yes. Okay. I used what's called interval notation here, so don't get surprised. Okay, this x is an element of AB can also be written as A is less than x is less than B, like that, using inequalities. Okay, remember that from grade 10 when you taught interval notation, set notation, and all this stuff. Yeah. So if you've got an interval AB, okay, if you've got an interval AB such that within that interval, if you draw a tangent, the gradient, if the gradient is greater than 0, then we say the function is strictly increasing within that interval. Because one function can both increase or decrease. Sometimes it can increase, then decrease, then increase. In the case of a cubic graph or a cubic function. Okay, so make sure you know that. Right, the next point. For all increasing functions, the gradient is positive. For all increasing functions, the gradient is positive. All right? Let me draw a sketch for that. Let me draw the sketch here. So, if I give you a Cartesian plane, let's just talk about, let's say, an exponential function like that. If that point is point B, maybe this point here is point A. Okay, we've got an A value there. We've got a B value. We draw a tangent like that. Okay. The derivative must be greater than 0. Okay. right? So if you want, you can add that in your book. That's a scenario. Remember, when we are talking about increasing functions or decreasing functions, we are referring to nonlinear functions. Okay, we are referring to nonlinear functions. We don't worry about the linear function because it is easy and very straightforward. Okay. Right. Decreasing function. Decreasing functions. Right, please write this down. A function f is strictly decreasing. The function f is strictly decreasing. The function f is strictly decreasing over the interval AB, over the interval AB if f prime of x, or the first derivative, is less than 0 for all x is an element of AB. Okay. Then you put a full stop. And then the next point, you must write this down. All decreasing functions have a negative gradient. All decreasing functions have a negative gradient. All decreasing functions have a negative gradient. Full stop. All right. Right, then the next heading. Next heading will put on stationary points. Okay, stationary points in the lower grades, that is 10 and 11, generally we call them turning points. Okay, in calculus, these two can be interchanged. Stationary point, turning point. Okay, stationary point, turning points. All right, can you please write this down? Always remember that the gradient of a function and the gradient of a tangent at a point are equal. Right? That is mt, that t, the subscript is for m tangent. Mt is equal to f of prime. If we choose a value of x there, they are going to be equal. So if you choose a point along a function, choose a point, draw a tangent to that point, the gradient of that function and the gradient of the tangent at the the point of contact are going to be equal. Okay. Now, the next point. At all stationary points, in brackets, turning points, at all stationary points, in brackets, turning points, the gradient of the function and the tangent are equal to 0. At all stationary points, brackets, turning points, the gradient of the function and the gradient of the tangent are equal to 0. When you put a full stop. Let's just draw a sketch of that. So what I'm talking about is this. If I give you a quadratic function, because we haven't done the graph of a cubic function as yet, right? At this point here, that's where you have your turning point. So it's a horizontal line. If you draw a tangent, it's going to be a horizontal line. Okay? Now the gradient here of the tangent is 0. Okay? Let me call this point A. Okay? Allow me to erase this. So this is going to be equal to f of A, and both are going to be what? Equal to 0. Right? We're talking about at the turning point. Right. Now, last year, when we were trying to find the turning point of a quadratic function, remember, I think you have two methods, but it's very important for me to connect the quadratic function and what we are doing now. It's very important. Last year, when we are finding the x value as a turning point, remember we use the formula x equal to minus b over what? Over 2a. That was one way to find the x value at the turning point. Or you use the x-intercepts if they were provided. Okay? If they were provided, because the turning point, okay, is actually a point in such a way that the axis of symmetry passes through the turning point for a quadratic graph. So, if you have the x-intercept x1, okay, so your x there was equal to x1 plus x2 all over 2. You remember that? Yeah. That's another way of finding the x value at the what? At the turning point. Now there's a third way using calculus, which you can now use from now on. Right? All you have to do is find the first derivative. You can use this when you're dealing with a quadratic function. If they ask you the turning point, you find the derivative, then you equate that first derivative to 0. It will be a linear function, remember? The derivative of a quadratic function is a linear. So you get a linear function, you equate it to 0, you solve for x. Okay, so you should not get stuck when we come to find the x value as a turning point, because there are now 3 methods of doing the same thing. 3 methods that can give you the same answer. Okay, those 2 from grade 10 and 11, and then calculus. Okay, and all solutions are provided when it comes to the memo, because people think differently. All right, then if I choose another point, say somewhere there, okay, if I draw a tangent to that point, okay, let's say this point here. Okay, I'm going to call the value of x at that point, maybe say b. Okay, please, you can choose any letter you want. Mr. Tuponda chose b, so that's my b. Okay, just to remind you, to the left of the turning point for this graph, it is increasing. Therefore, f prime of x will be greater than 0. Also, f of b, okay, f prime of b will be greater than 0. Remember, b is an x value. So if you substitute the value of b into the first derivative, which is a linear function, the first derivative of a quadratic function is a linear one. You substitute the value of b, you get your gradient. And that gradient must be positive. In line with the definition of an increasing function, I'm talking about that point. Then, if we have it on this side, we draw a tangent. Okay, let's call that point there, point C. Okay, at this point, the function is decreasing, which means the first derivative must be less than 0. And if you substitute the value of C at that point, you must get a derivative, which is negative. Okay, and obviously here the gradient is 0. And your gradient of your tangent plate is going to be given by f prime of C. Here it will be given by f prime of C. Okay, so I'm just using this diagram. We can have one with a minimum turning point, but the concept is the same. If you want, you can sketch the one with a minimum turning point. Okay. All right. Let me move on to another aspect now. Any questions? Any questions? Right, if you don't have any, okay, you need to be very careful about the shape of a cubic graph. Okay, it is determined by A. A is greater than 0. You start with a maximum turning point, then a minimum turning point. Now, it's not always the case that a cubic graph will have 2 turning points. Okay, 2 is the maximum, but sometimes it can have, it can only have a point, so a point which, so you can have a situation where a stationary point is also called the point of inflection, whereby it will look like this. It can look like that. You can have a cubic function, okay, which looks like that. Okay, so the shape that does not look like this one only, it can also look like this, depending on the equation. In most cases, if the shape is like this, it means B is 0, okay, and probably C as well. So it means you only have AX cubed plus D for you to have this shape. It's also a very much possible shape for a cubic function. Okay, now for this one, it's very unique. We are going to talk about some examples later on. That one there. Right? So this is the shape. Okay, now I'm sure you can see that both of them, when A is positive, they start as increasing functions. Okay, when A is positive, they start as increasing functions. That's very important. That can also help you to remember how the shape looks like. Okay, then let's move on to the next case. When A is less than 0, you start with a minimum, then a maximum turning point. Okay, or you can start from the top, it goes down like that. Okay, so you can also have a case like that. So those are the shapes. Okay, the shape of the graph is very important, as we were taught in the lower grades. Knowing the shape is very important. Okay, then let's move on to another aspect, which is the turning points. The turning points. The turning points. So that's number 2, turning points. Okay, in brackets, just write stationary point. Please write this point down. A cubic graph can have at most 2 turning points. A cubic graph can have at most 2 turning points. Right, full stop. At the turning points, the gradient is 0. At the turning points, the gradient is 0. At the turning points, the gradient is 0. Right, I want you to draw this. Okay, let's start with a function that has got the value of a which is positive. Okay, so you have your turning point there, another turning point. Okay, we want, let's call the value of x at that turning point, let's call it a, and the one at the second point, let's call it b. Okay, remember here, f prime of x is 0. Okay, and also here, f, in actual fact, you can put the value of a there, where there is x. So you can write f prime of a equal to 0. Put a there. Let's put a. F prime of a is equal to 0. And here, it will be f prime of b is 0. Okay. Please don't get confused. A and b are x values. Okay. Then, to the left of the maximum turning point, the function is increasing, which means f prime of x, it will be greater than 0. Right, and then on the other, and here it will be decreasing. Right, and there it will be increasing. So f prime of x is greater than 0. Here f prime of x will be less than 0. Okay, the next lesson will carry on from here. Carry on from turning points. Because we need the other case. Okay.